Welcome to our lecture on number theory. Today we are going to explore a fascinating mathematical puzzle that dates back thousands of years. We will learn how to reconstruct a single hidden number just by knowing the remainders it leaves behind when divided by several different numbers. This is the heart of the Chinese remainder theorem. Let us start with a story. Imagine you are an ancient general trying to count a massive army, but there are simply too many soldiers to count one by one. Instead, you ask them to line up in rows of three, and you notice two soldiers are left over. Then, you ask them to form rows of five, and three are left over. Finally, in rows of seven, two are left over. The Chinese mathematician Sun Tzu realized that by just knowing these leftovers or remainders and the sizes of the rows, you can figure out exactly how many soldiers you have. This theorem gives us the mathematical bridge to solve this exact puzzle. Now that we understand the goal, let us look at the mathematical rules. The Chinese remainder theorem guarantees a unique solution to a system of linear congruences. A linear congruence is simply a formal way of writing an equation about remainders. However, there is a strict condition. The divisors in your system must be pairwise coprime. This means that if you take any two divisors from your set, they cannot share any common prime factors. If this condition is met, the theorem promises exactly one valid solution that is smaller than the product of all your divisors multiplied together. Any other solution will just be a multiple of that total product. This brings us to the mathematical formula that solves the system. Conceptually, we are building a solution by adding together special terms for each equation. Let us break down the symbols. The variable a sub I is the target remainder you want for a specific equation. Capital M is the grand total modulus, found by multiplying all your individual divisors together. Capital M sub I is the partial product, which is the grand total M divided by that specific equation's divisor. Finally, Y sub I is the modular inverse. This acts like an on and off switch. When you multiply the partial product by this inverse, it turns on the remainder we want for that specific equation, while effectively becoming invisible to all the other equations in the system. If any divisor increases, the total modulus M grows significantly, expanding the distance between repeating solutions. Before we move on, let us see this formula in action with a concrete example. We will solve the exact puzzle posed by Sun Tzu. We are looking for the total number of soldiers, which we will call X. We translate the physical rows into modular arithmetic. Dividing by 3 leaves a remainder of 2, dividing by 5 leaves a remainder of 3, and dividing by 7 leaves a remainder of 2. We write these as a system of 3 linear congruences. Before applying our formula, we must check our condition. Our moduli are 3, 5, and 7. Since these are all prime numbers, they share no common factors. They are perfectly pairwise coprime, which means we are cleared to proceed. Continuing with our solution, our next step is to find the total modulus and the partial products. We find the grand total modulus, capital M, by multiplying our three divisors together. 3 times 5 times 7 gives us 105. This means our final unique answer will be a number between 0 and 104. Next, we find the partial products for each equation by dividing the total modulus by each individual modulus. For the first equation, 105 divided by 3 gives 35. For the second, dividing by 5 gives 21. And for the third, dividing by 7 gives 15. Notice that each partial product is simply the product of the other two moduli. Now we must find the modular inverses, which act as our mathematical keys. For the first equation, we need a number y1 such that 35 times y1 leaves a remainder of 1 when divided by 3. Since 35 divided by 3 leaves a remainder of 2, we are solving 2 times y1 equals 1 modulo 3. Multiplying 2 by 2 gives 4, which leaves a remainder of 1, so our first inverse is 2. For the second equation, 21 already leaves a remainder of 1 when divided by 5, so the inverse y2 is simply 1. Similarly, for the third equation, 15 leaves a remainder of 1 when divided by 7, so our third inverse y3 is also 1. We now have all the pieces to construct our final answer. We plug our target remainders, partial products, and modular inverses into the main summation formula. We multiply the three components for each of the three equations. The first group gives us 140, the second gives 63, and the third gives 30. Adding these together yields a preliminary total of 233. Finally, we divide this total by our grand modulus, 105, to find the smallest positive solution. The remainder is 23. Physically, this means the smallest number of soldiers the general could possibly have is exactly 23. Now that we have solved the puzzle, let us look at what this process represents visually. On the left, we have our original hidden number, 23. When we apply the modulo operations, dividing by 3, 5 and 7, we break this large number down into a unique fingerprint of smaller remainders, shown on the right as 2, 3 and 2. The Chinese remainder theorem is the large arrow pointing backward. It provides the exact mathematical bridge to travel from that fragmented fingerprint back to the original hidden number. It shows us how multiple small pieces of information combine perfectly to reveal a single hidden truth. Let us apply this to a modern scenario. Suppose a university server runs 3 backup tasks. Task A runs every 4 hours and finished 1 hour ago. Task B runs every 5 hours and finished 2 hours ago. Task C runs every 9 hours and finished 4 hours ago. We want to find out how many hours ago all 3 tasks synced up and ran at the exact same time. We set this up as a system of congruences, where x is the hours since they synced. The moduli 4, 5 and 9 share no common prime factors, so they are pairwise coprime. We multiply them to find our total modulus, which is 180 hours. Next, we calculate the partial products and modular inverses for our server tasks. For task A, dividing 180 by 4 gives a partial product of 45. Since 45 already leaves a remainder of 1 when divided by 4, our first inverse is simply 1. For task B, dividing by 5 gives 36. 36 also leaves a remainder of 1 when divided by 5, so the second inverse is 1. For task C, dividing by 9 gives 20. 20 leaves a remainder of 2 when divided by 9. We need a number that multiplies by 2 to leave a remainder of 1. 2 times 5 is 10, which leaves a remainder of 1, so our third inverse is 5. We are ready to plug everything into our summation formula. We multiply the remainder, partial product, and inverse for each of the 3 tasks. This gives us 45 plus 72 plus 400. Adding these together yields a preliminary total of 517 hours. To find the smallest positive time, we divide 517 by our total modulus of 180. The remainder is 157. Physically, this tells us that exactly 157 hours ago, all 3 server tasks ran at the exact same time. This shows how the theorem can look backward in time to find synchronized events. Now that we have used this formula, let us understand its real-world impact. The Chinese remainder theorem is not just an ancient puzzle. It is a vital tool in modern computer science and cryptography. One of its most important applications is in the RSA encryption algorithm, which secures almost all data sent over the internet. When computers decrypt secret messages, they have to perform math on incredibly large numbers, which is very slow. By using this theorem, a computer can break a massive calculation into several smaller, faster calculations using smaller moduli. Once the smaller answers are found, the theorem stitches them back together to reveal the final decrypted message. Let us review the key takeaways from today's lecture. The Chinese remainder theorem is a powerful method that allows us to reconstruct a unique original number perfectly from a set of its remainders. To use it, we must have a system of linear congruences where all the divisors are pairwise coprime. By doing so, it transforms complex problems involving massive numbers into a series of simpler, smaller problems that are easy to solve. Because of this incredible ability to simplify calculations, it remains an essential concept, bridging the gap between ancient pure mathematics and modern digital security. You now have a complete understanding of how this theorem works.